Okay, section 2, part D, or part 4. The final thing I want to talk about, as I alluded to at the end of the last video, is the effects of unit changes. So let's say that you have some data, probably a very large set of it, 20, 30, 40, 100 numbers, and you've computed mean, median, standard deviation, IQR, maybe even the quartiles, and then you change your units. You change from feet to inches or Fahrenheit to Celsius or something along those lines. And you don't want to have to recompute the new mean, the new median, the new standard deviation especially, and so forth and so on. So how to sidestep the process, how to shortcut. If you have the mean, median, standard deviation, IQR, maybe even the quartiles, min, max, why not, in the old units, then how to quickly derive those quantities in the new units without having to recompute them. The last thing you want to do, having found the standard deviation of all of the heights of the bushes in feet, is to find the standard deviation of all the heights of the bushes in inches. The long way, that is, by multiplying every number by 12 and starting over. Now you may think the answer is going to be obvious, but this is one of those points where people begin to lose it. I think it's visually very easy to understand, but the formulas sometimes confuse people. What it boils down to is the following. There are two types of unit changes. There is a rescaling. There is changing the size of the units, which you do with a multiply effect, right? If you go from feet to inches, then you multiply by 12. If you go from inches to feet, then you multiply by 1/12. Remember, multiply includes the possibility of divide, right? Dividing by 12 is the same as multiplying by 1/12. You go from yards to feet, you multiply by 3. You go from feet to yards, you multiply by 1/3, and so forth and so on and so on. On the other hand, you can also have a shifting effect. I could, for instance, add 5 points to everybody's grade, or put a 6-inch hat on everybody and measure their heights again so that you add the same number to everybody. There are also those types of unit changes where you just physically move the whole thing over by adding the same number to everybody, and that's the one you've got to be careful about. Put it together, and we have what we call, if you're interested, a linear transformation. That is, y equals mx plus b. The way that you can get the new units y from the old units x, you can either multiply everybody by some number or add some number to everybody, or both. So for instance, if you're doing feet to inches, 0 inches is 0 feet, right? So you just do 12x plus 0. That is to say, there's no shift involved. Nothing in is nothing out. 0 feet is 0 inches, 0 gallons is 0 quarts, and so forth and so on and so on. On the other hand, if I add 5 to everybody's exam, then we're talking about 1x plus 5. That is to say, x plus 5. You see what I mean? Not doing the shift is the same as b being 0. Not doing the rescaling is the same as multiplying by 1. But theoretically, you could be doing both. You could double everybody's salaries next year and give them a $1,000 bonus. 2x plus 1,000. And so forth and so on and so on. Now bear in mind, if you rescale the units, as far as the m goes, nothing in is nothing out. M times 0 is still 0. 0 cups is 0 quarts, and so forth and so on. But if you have a shifting effect, then you're moving the 0 point, right? Theoretically, if somebody got a 0 on the exam and I added 5 points to everybody, then they would get a 5, right? So 0 in, 5 out. So shifting involves changing the 0 point. A good example of where we've got both of these principles in play, where the size of the units are different and where the 0 point is different, is Celsius to Fahrenheit or vice versa. We'll look at that example a bit later, but let's start out with something a little simpler. So the bottom line here is that things that measure spread are not affected by shifts. Shifts do not affect spreads. Spreads are not affected by shifts. Let's think about this for a second. All of the things we've talked about in the previous videos here, all of the stuff that we compute in section 2, in a word, descriptive statistics, we haven't called them that, but that's basically what they are. The mean, the median, the standard deviation, the IQR, the quartiles, the min, the max. The book talks briefly about range, max versus min. All of those things are in the same units as the original, right? So if all of your data is in gallons, then the mean is in gallons, the median is in gallons, the interquartile range, the IQR is in gallons, the standard deviation is in gallons, Q1, Q3, min, max, all in gallons. However, there is a subtle distinction here. Remember that the average, the balance point on the number line, the median, the halfway point on the number line, the min, the left endpoint on the number line, if you like, the max, the right endpoint on the number line, if you like, the quartile, the 1/4 point on the number line, the first quartile, the third quartile, they're all spots on the number line. They're all tick marks on the scale. Well, let's see, I don't have a great picture here going. Well, let's take this one, the median, the mean, Q1, I'm looking at the red here, the mean, the median, Q1, Q3, min, max, they're all tick marks on this scale, whatever it is, 1 to 3, whatever they are, right? Feet, gallons. However, standard deviation and IQR are a little bit different, right? Standard deviation and IQR are not tick marks on the scale. IQR is the distance between two tick marks, the distance between Q1 to Q3. Standard deviation is the average distance from the center. So if we're looking at the red, and let's say this is Q1 and this is Q3 for the sake of argument, then this distance is the IQR. And maybe this distance here is, let's say, the standard deviation, the average distance from the center. It's a distance. It can't be negative. Of course, if you're talking temperatures, there's no reason the tick marks on the scale couldn't be negative if the units can be negative. But standard deviation and IQR can't be negative. They are distances. They are not actual tick marks on the scale. They are distances between tick marks on the scale. And that means that you can think about them a little bit differently. Yes, they are in the same units as everything else, gallons, etc. But standard deviation and IQR are not examples of a temperature. They're not examples of the height of a tree. They're not spots on the scale. They're distances between spots. And that means that they're going to work a little bit differently. They'll be affected in the obvious way by the multiply in the formula, but they won't be affected at all by the add in the formula. Things that measure spread, standard deviation, IQR, are not affected by the shift, by the add subtract in the formula. Subtracting, of course, is adding something else. I could take 5 points away from everybody's exam, plus -5. So that's the principle involved here. In symbols, it may look a little strange, but the mean, and just focusing on the top 4 here, the mean and the median are examples of tick marks on the scale. They're temperatures like any other, they're amounts of fluid like any other, they're heights of trees like any other, and you just run them through whatever unit change you've got. So if you double everybody's salaries and add $1,000, then you're going to double the mean and add 1,000. You're going to double the median and add 1,000. But the standard deviation and the IQR are only going to be affected by the multiply divide in the formula, not by the add subtract. So if I double everybody's salaries and add $1,000, I'll double the standard deviation. The 1,000 is irrelevant. I'll double the IQR. The 1,000 is irrelevant. I didn't plan ahead here, so I can't really show you the math, but let me just do it in words. If you add 1,000 to Q3 and you add 1,000 to Q1 and then you subtract, the thousands are just going to cancel. They're not going to affect your answer. It's a little less obvious with standard deviation, but it's equally true. I think visually speaking, this is relatively easy to understand. Take something simple here. Let's say for the sake of argument, I know the numbers don't justify it here, but let's say for the sake of argument that the blue is heights in feet and the red is heights in feet and the blue is heights in inches or something along those lines. Ignore the scale on the bottom. Then the principle that I'm going for here, of course, is that the feet numbers are 12 times less spread out than the inches numbers. But otherwise, you're getting the same shape. It's still people's heights, regardless of what you're talking about. So if I multiply every number by 12, let's say to go from the red to the blue, from the feet histogram to the inches histogram, if I multiply every number by 12, then it's going to be 12 times more spread out than it is. In this example, I'm basically doubling, but just to take an example. If I'm multiplying every number by 12, then the blue one is going to be 12 times more spread out than the red one. So in other words, multiplying will have the obvious effect on spread. If I multiply every number by 12, the IQR and the standard deviation are going to get multiplied by 12. But on the other hand, if I put a 6-inch hat on everybody, something like this, heights without the hat in blue, heights with the hat in red. All I'm doing, again, ignore the scale, all I'm doing is moving the whole picture right or left. Adding a number to everybody has this kind of visual effect. Add a positive number, blue to red. Subtract a number, add a negative number, red to blue. All you're doing when you add a number to everybody, a positive number, is shifting it to the right. Subtract a number, add a negative number, you're shifting it to the left. And you can see that that is going to affect, in the obvious way, anything that is a tick mark on the scale. Whatever distance I'm moving this over, the min gets moved over that distance, the max gets moved over that distance, the mean, the median get moved over that distance. The quartile, let's say, is here, gets moved over that distance, and his twin brother. But anything that measures how far stuff is from other stuff is going to be exactly the same number as before, right? This would be easier if I could hold up my arms and wave them around in class, but let's say that this distance is the IQR. Well, move the whole thing over, and that identical distance is the IQR over here. Alternately, let's say that this distance is the standard deviation for the blue, the average distance from the center. Well, the exact same distance over here in the red is going to be the exact same average distance from the center. The quartiles measure how far apart the quarter points are. The standard deviation measures the average distance from the center. They don't really compare. They're very different types of spreads, but they're both measuring how far stuff is from other stuff. So adding a number to everybody is not going to change something that measures how spread out stuff is. The blue and the red are obviously spread out in identical ways. They're just moved back and forth. So this means that the standard deviation and the IQR are not going to be affected by the add-subtract in the formula that represents moving the entire histogram back or forth. One final note on the formulas, note the light gray here. I am presuming in all of this that m is positive. It wouldn't make any sense for m to be 0. Turning every number into the same number would be silly. But I am assuming that m is positive. In other words, that it represents a rescaling. You know, feet to inches, inches to feet, multiply by 12, multiply by a 12th, but positive. Standard deviation and IQR, remember, are non-negative concepts. The answers cannot be negative. So if for some reason you had a negative m, that's the light gray here. If for some reason you had a negative m, then you would want to lose the sign on your answer. Keep it non-negative, keep it positive. The only example that I can really, a couple examples that come to mind, if you have points off on the exam, let's say it's 100 points off on the exam to actual grade on the exam, right? 100, y equals 100 minus x. 5 points off, 95 on the exam. 1 point off, 99 on the exam. 10 points off, 90 on the exam. Y equals 100 minus x. That is to say, y equals negative 1x plus 100. So there's an occasion of where smalls become bigs and bigs become smalls. When you have that flip around, just lose the sign. That's why I've got the absolute value here in light gray. Probably will never come up, but just for completeness purposes. Alternately, you could have something like how if you're swimming in a pool, you could have x going in, feet below the surface, y coming out, feet above the bottom of the pool, right? So smalls become big, bigs become smalls. In a case like that, depth versus height from the bottom of the pool. If you've got that kind of swapping around effect where you've got a negative m, then again, lose the sign. You probably are never going to encounter those kind of unit changes, but just for completeness purposes, I'll throw that in there. The presumption here in the dark, normal black text is that m is a positive number. Just be a little careful. So 3 examples. If I convert from feet x to inches y, that is to say if I multiply every number by 12, then I'm going to multiply the mean by 12, multiply the median by 12, multiply the standard deviation by 12, multiply the IQR by 12. Notice another way this problem could play out, apart from saving you time, is if they gave you summaries rather than data. They could tell you, without telling you the numbers, they could tell you that the mean is this and the median is that, and then make you go through it. So, apart from being a shortcut, it might be the only way you could do it. Example number 2, add 5 points to everybody's grade. Well, moving the entire histogram 5 one way or the other does not change how far stuff is from other stuff. So the new mean will be add 5 to the old one. The new median will be add 5 to the old one. The new standard deviation will be the same as the old standard deviation, and the new IQR will be the same as the old IQR. Then again, example 3, let's do heights of people in feet, and then let's put a 6-inch hat on everybody and then measure their height in inches. Oh, that's a typo there. Sorry, that's a cut and paste typo. What I really mean there is 12x plus 6. So in your mind's eye, you're looking at y equals 12x plus 6. Sorry, that was a rush job. So if y equals 12x plus 6, then the new mean is going to be 12 old mean plus 6. The new median is going to be 12 times old median plus 6, but the new standard deviation is going to be 12 times the old standard deviation. The plus 6 is irrelevant. And the new IQR is going to be 12 times the old IQR. The plus 6 is irrelevant. Again, pretend this is 12x plus 6. That's a cut and paste typo. The real world example that has both a shift and a spread, I guess we're done with that. The real world example that has both a shift and a spread, and this is in the class notes online, is the Celsius to Fahrenheit conversion formula, or vice versa. I think probably this will be a little easier. You can do it in either direction, but I think it'll probably be a little easier on the eyes if we do Celsius to Fahrenheit. First off, a degree Celsius and a degree Fahrenheit are different sizes conceptually, right? freezing to boiling. 32 to 212 is a lot more numbers than 0 to 100. So a degree Fahrenheit and a degree Celsius are different sizes by a factor of 9/5. But also 0 in and 0 out are not the same. 0 in Celsius is 32 in Fahrenheit. That's freezing. 0 Celsius or centigrade is freezing. 32 Fahrenheit is freezing. So 0 in, 32 out. You don't have 0 in, 0 out. There's a shift going on. The meaning of 0 changes. What 0 is, 0 in the one scheme of things does not represent the same quantity as 0 in the other scheme of things. There's a shifting effect going on, right? So 9/5, so Fahrenheit is 9/5 times Celsius temperature plus 32. So the bottom line is that if you've got these various things we've computed for a bunch of temperatures, mean temperature, median temperature, standard deviation of temperatures, IQR of temperatures, then the mean temperature, call it F bar and C bar here, the mean Fahrenheit temperature is going to be 9/5 times the mean Celsius temperature plus 32. The mean and median are just tick marks that get run through like anything other. The mean temperature and the median temperature, min, max, Q1, Q3 temperatures, are examples of temperatures. So of course they get run through the highlighted unit change formula. But standard deviation and IQR are not examples of temperatures. They are distances between temperatures. So the shifts don't affect them. Standard deviation of temperatures in Fahrenheit is 9/5 times the standard deviation in Celsius. IQR, same principle, 9/5 times the old Celsius IQR. Okay? The same principle would work the other way, although it's not necessarily in this form. I don't have it written down, so let me just do some quick calculations. If you wanted to go the other way, then you would have C equals, subtract 32, and then divide, and then multiply by 5/9. So if you wanted to go from Fahrenheit to Celsius, you would subtract 32 and then divide by 5/9. Parenthesis F minus 32 times 5/9. Same principle. The 5/9 gets done to everybody, but the subtracting 32 doesn't get done to standard deviation and IQR. Now, if it's bothering you that F minus 32 in parentheses times 5/9 is not quite this form, well, don't worry about it. The bottom line is you do the add subtract in the formula. You do the multiply in the formula for everybody. The multiply divide in the formula you do for everybody. The add subtract you only do for, you don't do for standard deviation and IQR. But if it's really bothering you, you can multiply it out. That's 5/9 F minus 160 over 9 or something like that. So you can put it in this form just with a little distribution. But I think going this way, Celsius to Fahrenheit, is a more straightforward example. Now, it always freaks people out. I could care less whether you know off the top of your head how to compute Celsius to Fahrenheit. It's only an example. This is not information that I presume you know. It doesn't pertain to a statistics course. It's just a real-world example of where we have both effects going on here. So I'm not presuming that you have how to convert temperatures formula at the tip of your fingertips. It doesn't really matter for an online course like this, but just FYI. So there is section 2, finally. And next up will be section 3. That is another long section, and it's another it's a very important section. It's probably the most important section of the course, so I want to go through it relatively slowly. There's a lot of resources here. In addition to the highlight section, there is an additional review of how to do things in a practical way. There's also some YouTube videos. I hope that link still works, but I'm afraid to check it out while I'm recording. So we'll talk about that next time. Section 3, very important section. From there, things take a bit of a turn, and we'll gradually pull it all together as we go. So that is Section 2 done.